Week 5, Lecture B. So 2 lectures per week, Lecture B. And this week we are going to focus on performance specs, specifications, and performance limitations. Okay? So these two are very important. So we usually learn what do you want. That is, oh, I want this specification, this specification. So when you suggest a specification, you should at the same time should also understand what is the best achievable specs, okay? Those specs. If you don't understand this, you are at a risk. You overpromise, yes, I can do it, but in the end, you violate this best achievable specs. You promise something that is too much. Your system cannot achieve at all. So lab 1 is to ask you to address this issue, okay? Address this issue. And in that case, our linearized transfer function of a system is something like this. So A, B greater than 0. So you have a system with one unstable pole with one non-minimum phase, zeros. What are you going to do? And how bad it is? And without designing any controller for this, we already can tell in advance what is the best achievable limit, something that you cannot do better than this, okay? So understanding this thing is very important in control system design. And this is not appreciated in many of the control classes, okay? So in robust and optimal control, as I said last lecture, 2 questions. What do you want? And what do you know? Okay? Do you know? Or what do you have? Okay? Do you have? So these 2 questions are fundamental. So I said control is an art of trade-off. Okay? We know that Donald Trump has a book. It's called Art of Deal. Okay? But control is different. You get some benefits. You need to ask what you paid for that benefit. So it's a trade-off. Okay, trade-off. Okay, so nothing is fundamentally. So in the beginning, I showed everybody that for sensitivity, dirt. So I hope everybody will watch that movie I put there. It's called Gunther's Stand. Okay, Gunther's Stand. Okay? And there's a YouTube video. Okay, video behind that. So I know how that YouTube video was made. Okay, I'm the person behind that video that I pushed somebody who has that analog recorder and convert to digital and put on the YouTube. I constantly pushed that. So then finally it happened. So to the record. So you know that video? I'm one of the persons behind it, pushing that one happen. After several years persistent pushing, made it happen. And it turns out this is excellent thing. If you never watched his talk, you should not claim you are a hardcore control expert. He's with Honeywell. Okay? Honeywell. Yes, Honeywell. Okay. There are about less than 10 Honeywell fellows. He's one of them, and I know there's another fellow. Okay, So he must be really good. Okay, he has a lot of insights about control. So he has lots of control insights. Okay, but a lot of control insights for many of you. You need to learn. Okay, the insights. So this type of fundamental limit is one of the aspects of the insights. And usually people will talk about insights in time domain and insights in frequency domain. And I think that many of our current generation of control scholars are lacking of frequency domain insights. Okay, frequency domain insights. So so that's why today we're going to spend the half of the time focusing on Bode plot. So if I say Bode integral formula, okay, you don't have a very good sense, okay? Especially you start with math as your major, okay? You don't have that insights for that, okay? So let's start by doing a body. So let me do a body plot for you, okay? Let me do a body plot. Body invented body plot, okay? But the question is how he even know he needs to invent body plot. So today I'm going to tell you the reason. I believe that's the reason behind it, okay? But let's do that. Say for example, I'm going to do one nerve Ts plus 1, okay? T plus 1. So this is, when S is 0, then this is 1. When S goes to infinity, and this is 0, right? So this is 0. So this is a typical what? A low pass filter, okay? Low pass filter. Okay, low pass filter. So we usually talk about this, this is G of S. So then the frequency domain is J omega. So I already told you why we replace S with J omega. Then we can get Fourier transform. Okay, so that's called a maximum modulus theorem, right? Maximum modulus theorem. So in this thing, we always can write the real part plus imaginary part n times j, right? We also can write polar form with magnitude and the angle, right? Angle. So I will put the j here. J. Okay? Okay. Okay. So if I do, then I'm going to draw two plots. One is mag. Mag is this one. This is called mag. Okay? Mag. Okay? So I do magnitude. I do 20 log 10. Okay? 20 log 10. So this is called dB. Okay? It's called dB. So when this is 1, when it is 1, okay, so this is log omega, okay, log omega. So when omega is 0, that means log 0 is minus infinity, right? Minus infinity. So when it goes that, I'm going to put the body plot will be 1. 1, then this is 0 dB. So this is 0 dB. So I will be 1. Okay, this is 1 basically. Or 0 dB here. Or I'll go to 1 until to a point. I know that eventually I'm going to go to 0. 0, that is, log 0 is minus infinity, is something here, right? Something here. So what I'm going to do is something like this. I'll do that. So then I'm going to have a transition at some point. So this is my transition. So I draw this one is called asymptote. So this is called asymptote. So this point is called omega c. It's it's a turning point. Okay. Sometimes we'll call this as cutoff frequency. So this omega c is nothing but, so you should write this into a j omega way. You should write in this way. S divided by, sorry, so you put this way. Put j omega divided by omega c plus 1. Okay? Plus 1. So in other words, if I do this, this is my S. So then 1 over omega is c. 1 omega is t, right? So this one should be 1 over t. Okay? Be careful. Every time when you say this is 1 over t. 1 over t. Yeah, this is 1 over t. Okay? If we write this way, then this is the breaking point. This is the breaking point, also called breaking point. So this is magnetic body plot for a low pass filter. But what if I say I have a bracket to the power of 2? Okay, it's the same thing. Okay, you still have this one. You still go to infinity, but you go to infinity in a different way. So that is the way you go to infinity. So this is 1, this is 2. When this n is 1 and 2. Okay, this is 1. So you can see that relative degree here will depending on, this is called roll-off rate. So in this case is minus 20 dB per decade. In this case is minus 40 dB per decade. So depending on that, we can also do the phase. I don't want to do the phase now because Bode said for a minimum phase m dot p dot, okay? Minimum phase means you have no zero living in right half plane. So this is a minimum phase and strictly proper. Okay? For minimum phase, this complex function, okay? You only need to do one Bode plot, magnitude. And then the phase can be inferred by using his Bode integral formula. That is in your handout. That's the procedure of how to prove it. Okay? You only need a magnitude, you don't need a phase. Or you give a phase, you don't need a magnitude. So either way, you only need one of them. That's the beauty of Bode integral formula. Okay? Okay. So remember, you need to put this is called standard form. So you can see what is the breaking point. Okay, breaking point in here. So I gave Jose, you remember? I gave a PhD like S plus 10, like S plus 1, S plus 100 squared, and I want you to draw a Bode plot for me. So if you starting from here, that would be wrong, okay? What you really need to do is you do S divided by 10 plus 1, and S divided by 1 plus 1, S divided by 100 is 1 squared. So you have 1 divided by 100 squared, okay? You have 100 squared. Okay, so you have 1, you have here, you have 10. So then you have 10 to the power of minus 3, right? Yes. So then you have this game come out, okay? Then what is the breaking point? I call this is a breaking point. Breaking point is here, breaking points. So that would be 1, 10, and 100, okay? 100. If you have something here, then instead of going, then you go up, okay? Up. This is a plus 20 dB per decade, okay? So in here it should be 10, okay? It should be 10. But in here you have 1, and here you have 100. So you should have 100, you have something here. This is minus 40 dB per decade. Then this one here, you have something, so this is 1, right? So you have minus 20 dB per decade. Okay. 110. You have another one here. You have another one here. That is S. What is S? S will pass through one point, meaning one point, meaning, so this is like minus 10, minus 100, minus 1000, keep going to minus infinity, okay? So then you should have something passing through one point, because you have omega is 1, okay? Then this is also 1, okay? Also 1, okay? And then so they will pass this point. So basically you have another integrator like this, the red line. This is the integrator. And because of that, you do log, you just do, so the overall magnitude should be something like this. So you come down from infinity, you also go to infinity. Until to this point, until here, you have minus 40, because minus 20, so you have not going this minus 40 until to this point. Then you do, you have plus 20, so you do something parallel to this until to this point. Okay? So you have so you have minus 20 here. So this is a minus 40, minus 20. And then to this point, then you have a minus, so you have a minus 60 here. Okay, minus 60. So this whole thing from here to here to here to here, that's your overall magnetic body plot. Is this right? No, wait. Don't forget about this. So you have a minus, so you have 20 log is a minus 60 dB. So this one will add everything up. So basically you go down minus 60 dB. So this move everything down, minus 60 dB. Shift everything down, minus 60 dB. So that's why how you do the body plots, right? Okay. So again, I don't need to draw the face. The face can be inferred from this one because this is minimum phase. Okay, minimum phase. Okay. Minimum phase. So if you read the handouts, the first line, I think you will have trouble to understand this whole thing. Let me guide you through to read this one. Okay. So I'm just warming you up regarding frequency domain, body plots, and he invented this one, but I didn't tell you why he invented it. Why Bodhi invented the body plot. Okay? Okay, but we are now doing everything to take it for granted, all right? So let me summarize what you learned. Okay? Breaking points, this is also called a standard form. Standard form. And you can see that you do this, all this, so then this one becomes what? Becomes dimensionless. Make sense? So it's more beautiful. Okay, dimensionless. So this one and this one become dimensionless. Okay. So what I'm going to do now is to help you to get this body integral. Why we have something very strange. Okay. So I'm going to erase this one. You want to take a picture of it? So before I erase it. So body plot in 15 minutes. Okay. Yeah. Probably is a good idea. I did it very fast. You have learned several concepts like roll-off rates, like minus 20 dB per decades. What is a decade? It's this one. 1 to 10, 10 to 100. This is for so dB per if you put decade is in Chinese is 负20分贝每10倍平乘 okay range of frequency. So all these languages are not very familiar to the modern generation, okay? So, but it's very needed that you need to do a control insights in frequency domain. So right now you are giving A, B, C, D and play with all the state space. You lose all this type of thing. And this is fundamental. And the industry, as a Sina can attest, industry people, they're still in this age. If we don't explain them well in frequency domain, they are not going to use it, okay? I'm going to erase this part and start to get you to, okay, also you should watch Gunther Stein. In 2002, I started to push them. I pushed about 5-6 years. So then they converted to digital. So when I read Bodhi's real book, the old book, when I read it, the most difficult thing is for me to understand why he invented Bodhi plot. So here's why. Okay. So we all know that, of course, we are talking about size of, okay? Everything is size of. We are going to show slides that talk about MIMO, okay? The MIMO, you know that you need to add directions, okay? So you have a G of S. We said that we put G j omega, and we put E, the angle of G j omega. So that's what we want, okay? So we know that. What Bodhi did, original contribution he did, is he said, hey, let me do this. Let me just do a natural log of G of S, okay? Instead of studying G of S, I do this. And through different manipulations, as you can imagine, that it is always possible to write this in this log in another form is A of S plus B of S. Okay? Well, he said that the A of S is the odd part. Then this is E. Okay, so this is the even part. This is the odd part. Let's say, for example, you have a polynomial expansion, or so you can always do that like Taylor series expansion. But in complex analysis, it's called Lorentz series expansion, okay? But that doesn't really matter, okay? So you just agree that this can be written in two parts. One is even, one is odd function part. So, but you can quickly say that this is nothing but you have a log G j omega part and plus the angle of G j omega. So isn't this interesting? If you study this thing, okay, then in the end you can see this is the Bodhi plot, right? So that's why you need y-axis. You have to be a log. By the way, log 10 and natural log they only have a difference with a constant, right? That doesn't matter to our case here, right? It's just log. Okay? I use n as a natural log, so I showed up in here, right? So, but be careful, I have a j in here. I have a j in here, okay? I have a j. I have a j in here. And so I want to show you that this j is not going to go away. This j is here. So you have this j here, right? J here. And remember, this all real. This all real, okay? And what we are going to do, even and odd, then when we replace S is j omega, when we have even, then this is real. When we have odd, this is imaginary, okay? It's imaginary. So in other words, or if I can study log GLS, so basically, this is goes to this. This goes to that. So if you check even part of the log, is the log of magnitude. Odd part of this log, complex function, it is phase. So it becomes like, oh, this is a magnitude, this is a phase. So beautiful, right? Yes, it's very beautiful. So they call this as theta. Call this theta. This is just notation. Theta of S. So that's exactly the notation we have in this appendix. This appendix is from a book. This is a great book, okay? This is Boris Luria, and I believe he's in JPL, okay? I have a PDF of this book, JPL. And why this book is unique? All the other books, they try to interpret 1947 Body's book using their own language, their own symbols. So we read today's textbook, the symbols, and we read Bodhi's book, it's very painful, okay? I suffered a lot. I need to have some correspondence list of symbols. So eventually I get rid of the new symbols and follow Bodhi's symbol. Then I start to appreciate Bodhi's work. And this book, uniquely, totally following Bodhi's symbol system, okay? Everything it uses, like in Bodhi used the log G of S is theta of S, okay? Use everything exactly the same notation as in Bodhi's 1947 book, okay? So if you read this book, then you go back and check Bodhi's original book. No question about it, so it's very comfortable. And so far, this book is very successful to me. Okay, very successful. So if you understand, so you can see in this. So in here, they're talking about derivation of body integrals. Okay, body integrals. You don't find anything like that in any other book, okay? They don't have the proof. They just tell you, hey, here's the relationship, you use it, okay? And he derived it. So I made a copy to you as a souvenir. Challenge yourself to see whether you can follow. But you need some complex analysis knowledge, like path integral, okay? Like Lorentz series expansion, analytic functions, and so on and so forth. So the key part is the equation A4.10. So is this one, okay? Appendix 4, equation 10. And again, that you are now recognizing A is magnitude, B is space, okay? A is magnitude, B is space. So you plot A versus log omega in Bodhi's magnitude plot, you plot B over that. So if I want to find out, so if I already have A, a curve of A, magnitude plot, then given any point, what is the phase? You can use this integral to get it, okay? And you should not get confused or intimidated by this complex equation. And they arrived here from very simple definition from the beginning. Okay, so it is actually very simple. So you start from here, okay? From Lorentz series expansion. So, all right. So I don't think it's hard to follow. Okay. Okay. So that is the first part of the lecture, talking about body's integral theory. Okay.
Dr. Chen, you said the magnitude part is even, or even or odd, whatever, but based on the plots, because even plots should be like symmetric with respect to the y-axis, right? But I mean, I don't see how it is even in the plot.
It's an even function of omega, not even function of log omega.
Okay, even function of omega, not log omega.
Yeah.
Okay. Yeah, I should check that out. Yeah, sure.
Okay, that's good. That's good. But that's not the main point. The main point is body was genius in terms of doing this. I think it's an 80. That's it. It has a very nice physical interpretation as well. If you so in chapter 3, and the main contribution of body is instead of study transfer function g of s, he said let's study theta of s. That is the natural log of the g of s. That's his original idea. Okay. Then from there he invented the body plot. Okay. And so the key part of the answering the question why body needs to invent body plot, because he feels like studying the g of s transfer function is very difficult. So what he said, oh, let's do natural log of g of s and study that. Then we study body plot. Okay, so let's go back to our modern world. Feedback properties, we talked about gain of 6, gain of 4, giving gain of 16, right? 4 by 4. So we get used to the notation here. I want to remind you that everything here is vector, okay? Every signal here is a vector, okay? Every signal here is a vector. And we need to differentiate between input sensitivity, output sensitivity, complementary sensitivity, input complementary sensitivity, and output complementary sensitivity. So the reason we do not use closed loop transfer function matrix anymore, we don't use that anymore, is because we want to differentiate, focus on sensitivity, okay, and focus on one minus sensitivity is called complementary sensitivity function. So if you keep using complementary sensitivity function instead of closed loop transfer function, then that means you are living in a higher class. Okay, you understand the system better, you know. Especially in the MIMO case, it makes more sense to talk about complementary sensitivity function like that. And this is the sensitivity due to your command, okay, due to your command. That's why TO here, that's your response due to your command, or due to your noise. I derived the last time there. That is also very interesting in the sense of case. But here you just need to be a little bit more careful regarding dimensionality, compatible question. So don't write this to this side. So it's always a matrix and a vector. Okay. Okay. And when we talk about vector by default is a column vector. Default is a column vector. So it's column. So this is a matrix and a column. So this is also a column. So n by 1, right? Maybe you should use m inputs. Okay. So n has to be the same as r, the size. Okay. R and so on and so forth. But this is still problematic to me. If y and n they have different sizes, that's not possible. Okay. And if input and output is not the same, then you cannot do minus here as well, right? Make sense? So in other words, are we assuming R has to be the dimension of R and Y should be the same, so the whole overall system is square? Okay.
Maybe because y is our output and r is the set point, is the desired output, right?
Yeah.
So we can say.
So that square requirement is something not right. So in reality, you definitely will have a system, you have commands like this, you have output like that. So the number of inputs and outputs may not be the same. Okay? May not be the same. So what are we going to do? So there are some papers published under the title of called non-square systems, okay, like robust control, like RMI or whatever to infinity for non-square systems. I think idea is still to make it square in certain way, okay? Make it a square system, so in and out at the same number. So you can draw this picture, otherwise it's wrong, right?
But is R the input here? Because R, I don't think R is considered as the input here. Maybe like U is the input, Y is output, but R is the set
Let's say
point.
reference.
R is reference. It's the desired output. So we can.
I think your question is very good. So when we say input, what do you mean input? Input to whom?
To the plan.
If you input to the plan, that's called actuation signal. It's a control signal, input signal. So input could be from, input is more general. It could be from command, could be from disturbance, could be from noise. They are all inputs, okay? So yes, we need to be careful. Don't cause confusion when we use R is an input, but there are other inputs. But specifically R is called command or reference or set point. Okay? Command. So this is input. Okay, this is also input. So this is what? This equation is called superposition principle. Okay? Superposition principle. So when you study how the output respond to your input here, you can treat others as 0. Okay? Okay? Then only focus on this. So same thing for U and the UP signal can be written in this form. Okay? And don't memorize this, so you can just go to the textbook, you just do simple derivation, you will get it. So the fundamental idea is I want to follow my command reference. Okay? So the sensitivity should be small. Okay? So this should be small. Okay? It should be as small as possible so that I can attenuate the D. So if this one greater than 1, It's called amplification. If this one less than 1, or if below the 0, the sensitivity below the 0, 0 dB, okay, that's less than 1, it's called attenuation. So I want to attenuation, okay, less than 1, less than 1, not less attenuation. I want this one also attenuation, less than 1. I don't want this, but I want this one to be close to 1. Well, close to 1, that says close to 1. That means this one close to 1. That means SI close to 0. Okay, okay, close to 0. Then it means when you do log dB is also less than 1, right? So SI, S0 are all should be less than 1, which is here. So that sigma bar SI should be less than 1. Okay? And also sigma SIK should be less than 1. So this is called disturbance rejection at the plan output. So but visualizing, we can say this picture. So in low frequencies, I want my loop gain high. Because remember, the sensitivity is 1/1 plus L for size of case. But for the MIMO case, it's just I plus L inverse. Okay? And we cannot do a body plot for each individual one, so we just pick up 2 representatives. One is sigma bar, one is sigma underbar. Okay? So this is maximum singular value of a matrix. L is a matrix. Okay? L is a matrix. So this is a minimum singular value. So both of these worst cases are within my constraints. Then I have peace of mind. Everything works fine. Okay? So this is called desired loop shape. This is a rough requirement. So you have to satisfy this. Otherwise, it's not satisfy your design specs. Okay. So coming back, so we're going to see this term, PK. Okay, PK. Okay. And KP. Okay, KP. They should be greater than 1. Greater than 1, meaning the higher the better. Okay? The higher the better. But on the other hand, in the end, what you really can tune or change, you only can do this guy. The K you can do. You cannot change P. The P, you cannot do it. It's your plan. You want to control it. It's there already. So the K is the one you can play with. So just you know, that's why design a K to satisfy this type of desirable loop shaping is the basic requirement we need to satisfy. But in many cases, doing this type of feedback property in terms of loop transfer function, it may not be enough. Because there are some what we call domain knowledge, saying that, oh, I know my signal is mainly in this frequency range. If you can suppress that, that would be good. I don't care anything beyond that frequency range. How we can deal with that? That is because that is to add the weighting filter here. So all the W's are called weighting filter. Even you can add the weighting filter for the feed or for the command signal. So sometimes this is a specialized area. It's called command shaping. Command shaping. I would like to say it's like command cheating. So your system is not going to follow this signal, but it's following this signal. So they're called command shaping. Command shaping. I believe that's a trick. It's still useful. Why? Because when your system is already designed, you are not allowed to even touch this. Okay? What you really can do, you try to fool the system. I think Sina has done something on that. It's excellent. Yeah, this is basically you instead of following this, you add this filter and change this one, and then in the end, overall, we can get a satisfactory result, which is fine. It's very fun. And interestingly, I told you last time, a signal is a signal. A system is mapping between two signals, and a signal's transfer function is the signal's generating system. Okay, this is mouthful. Now I'm writing this. So you have a signal, right? You have a signal, and this Laplace transformation is D of S. Okay, and I want to know that what is who generated this guy? There must be a system. What is the system? The system has a transfer function of D of S. Okay? D of S. And this system, it will generate a dt. But with what as the input? This impulse. Okay? So that's why I'm saying that a signal is a signal, a system is a system. A system is a signal between signal. But the signal could be the system itself, if we understand it this way. Okay? So in other words, I'm always trying to think about that way. We're starting from delta, okay? And I assume I know D of S. I assume I know D of S. Then life will be easier. So this is the story. Okay? So if I say, oh, my D is delta T, okay? Delta T, and eta transverse is R. That doesn't matter. You don't have to be all the way one. Okay, it's not possible to do all the way one. You have to normalize it. Okay? So this thing is some sort of normalization. Okay. Now you can see according to what? According to what we learned regarding time domain energy. This two norm is integration, okay, integration. And also this is frequency domain in H2 space. You do, so all the W, S, and D transfer function matrices. So this in terms of S, then you integrate along omega to minus infinity to positive infinity. So this is exactly what we call Parseval's identity. So in time domain, you have energy. You have frequency domain, you also have energy. So these two should be the same. Okay? Basically saying that. So in other words, this ISE is same thing as like two norm, okay, of the transfer function matrix. Okay? Of the function matrix. So I told you why this is important. Because you know this one, okay? You know this one. You already know this one. But you don't have a E of t yet. If you need an E of t, you need to solve everything. You need to simulate it. So you can get this done without solving the system. That's the beauty, isn't it? Yes. So this is the beauty. So that's why Parseval's identity is important. Okay? But here we haven't addressed the robustness question yet. We are talking about performance in H2. But we also can do H infinity form. Okay? H infinite form in terms of induced norm from the two norm. So you can see basically it's along all directions. The magnitude is less than 0. Then in all directions, then you can, worst case, the suprema of this one, the smallest maximum, is the H infinity index, the norm, okay? So everybody knows this. So we can also say this is an arrow, worst case arrow, this is worst case control energy, okay? Control energy. So then usually we need to combine them, arrow and control energy. So that's why you have this one. So rho is the weighting factor. So this is a possible, so this is called mixed sensitivity. So remember, S is sensitivity, weighting is just the weights, okay? So these are called mixed sensitivity, okay? Mixed sensitivity. All right, so, so let's come back to here, body scaling phase relationship. This is something we have seen. We have seen this. So it's basically we talk about we have G of S. Here G of S is L of S. Okay. We're talking about Seisel case here. So when you have L is like control and plant add together. So it's C times G or K times P. So L is a loop transfer function. Okay. So again, I want you to recognize this. So L is a loop. So L usually is a C times P, or in our category, K times C times G is K times P, the same. Okay. So then 1 plus L, 1 over 1 plus L is my S. Okay. And T is my complementary sensitivity function is L divided by 1 plus L. And this one, in many cases, we happen to know this is called closed loop transfer function. Okay? But I prefer from now on, in a minor setting, we call this as complementary sensitivity transfer function. Of course, transfer function matrix. Okay? Complementary sensitivity transfer function matrix. So it's a matrix. All right. So now we don't feel this equation is so sudden after I explained to you. So basically, this is talking about the slope. About the slope. Like you have log L. Log L is the slope. D, dV. The V is actually a log omega. Okay, log omega. So its x-axis is log omega. Y-axis is log L. So y-axis is log L. X-axis is log omega. So dy dx. So this is body plot minus 20 dB per decade. That is a slope. Okay, slope. It's a slope. So this is basically body plot slope. May not be exactly the minus 20 dB per decade in many cases. Sometimes maybe 20 dB per decade, maybe minus 40 dB per decade, depending on the relative degree, and so on and so forth. Okay, depending on which frequency band, depending on that. In the transition, even like that. Okay. So this is this mu or v is defined by log omega. So you can see here, the x-axis is supposed to be dimensionless. Okay, dimensionless. But that didn't change. Basically, you put the body plot, you shift left or right. It doesn't matter. Okay, doesn't matter. So you need to have the omega 0. But you can say, oh, I didn't do that. You can say, oh, I selected omega 0 is 1. Make sense? Yeah. So you can say omega becomes still this x-axis becomes dimensionless. So you should think that way. Okay? And of course, here, natural log Ln and log 10, I believe they are also the same because only a difference of factor, constant. Okay? So, which must not be too small. So here, this is the angle. This is the angle. If you, so that's the, so you can see if you are giving a body's magnitude plot, you will be able to compute the angle, okay, the phase, okay, this giving omega 0. If we want to change another omega, you can scan the omega, you'll get the differential, this one here, okay. There's a figure to show this. Where is the figure? Okay, I think in this one here, I have a figure to show you. Yeah, this is on our textbook. This is on our textbook. So you may wonder, this term is very odd. So you can see before this function here, there's a slope. This is slope. This slope is at this omega 0, okay? This omega 0. And then the other term, log and hypercotenant v divided by 2 absolute value. Consider this as what? A weighting function. Okay, a weighting function. So what is the picture of this thing in the yellow weighting function? It is actually in here. This weighting function is like this. So this is the weighting function versus this nu. Okay. So this is, so at this when nu is 0, that means when omega equals omega 0. So we add very high weight on that, otherwise we just decay. So that makes sense, and this symmetric, okay? Symmetric. Okay? So suppose that I have a K, I have a P, then I factorize like zeros, poles, and so on and so forth. So I have a, so you can see if S is 0, then everything is a 1 in the front, okay, in the front. So this is just an assumption, okay, just an assumption. So you can see here, okay, here. So this is kind of like non-minimum phase filter, low pass, okay, low pass. So you can see when S goes to, when s goes to 0 is 1, okay? When s goes to infinity, it is also magnitude is 1, okay? So it's 1, all the way 1, okay? All the way 1. What's difference is the phase, So we just assume that the loop transfer function has two parts. One is minimum phase, one is non-minimum phase, okay? Non-minimum phase. Then you can see these zeros are, s is z1, z2, these are. But we assume that we pair it with s plus z1, s plus z2, okay? And see what I mean? Say for example, if we don't immediately see this one, I'm going to show you one. See? I have a s minus 1, s plus 2, s plus 3. I have a system, is area of s, okay? Area of s. Maybe I do s minus 4, okay? S plus 5. So, which is okay. So what I do here is, once you have this one, you pull out s minus 1 here. No, it should be plus 1. Because the DC gain should be 1, okay? It should be minus. Okay? Remember, when we say s minus z1, so that's actually wrong. Because the DC gain is minus, which is usually DC gain is 1, positive 1. So what you do is minus s plus 1, okay? Minus s. So what I do here is I do minus s plus 1, and I pair this one with s plus 1. Then I do minus s plus 4, I pair this one with s plus 4, okay? But you borrow this one, you return back. So you have s plus 2, s plus 3, s plus 5. So in other words, you have something not, this is RHP zeros. You replace RHP zeros mirrored to, you have something here, you mirrored to here, right? So this is mirrored, right, of this. This is also mirrored here. So you put this one here, put this one here. And they are all stable, you can cancel out. So then you focus on this one, which is minimum, the error minimum phase. And then we want to understand what's this, okay? Let us only do one thing, okay? Say like s plus minus, so what is this? So if I do j omega here, it's minus j omega plus 1, plus j omega plus 1. So this one will give me magnitude will be square root plus 2, 1, and here is a square root plus 1, and here you have arctangent. It's tangent minus 1 minus omega, and minus tangent minus 1 omega. Because this is a denominator, so I need minus the face, so everything will be like this, okay? Magnitude and phase. Magnitude and phase, e to the power of j, phase, right? Magnitude and phase. So magnitude is always 1, it's only phase is different. Okay, so if I draw body plot of this guy, it will give me all the one, magnitude is 1. All the way 1, no matter what omega you put in, right? And what is your phase, okay? So let's see. When omega is 0, everything is 0, right? So I start from 0 degree here, and when omega is infinity, so this is minus 90 degrees, right? Minus 90 degrees. And when omega is infinity, this is 90 degree. This is minus 90, so it's a minus 90 degree. So it's in here. So it's eventually, when this is 1, then is what? Minus 45 degree. Minus, this is a minus also 45. So omega is 1. So you have 90 degree, minus 90. So you have, so if something, you have something like this. So this is your phase. This is your phase. So from 0 to minus 180. So this guy is bad. He's always, he didn't do anything magnitude-wise, but he's always drag you, delay. Okay? Delay is no, phase lag is usually bad. So you don't really like that. Okay? Didn't do anything good for your magnitude. So you can see this type of thing have k such thing, then I know that everything is 1. So everybody is dragging the phase, Okay? So this is the phase. Of course, when I do the phase at that point, without these terms, things will be easier. But with these terms, the phase is still lagging. Okay? Lagging. So that is what we had before. But we need to correct it if we have non-minimal phase. Make sense? Because that equation, this equation, is only true when everything is minimum phase. You don't have a 0 living on the right half plane. If you have something living on the right half plane, this body's integral should be looking like this. These are the terms we need to add, meaning we need to add more phase to it. That's why we call this non-minimal phase effect. They just give you more phase. Okay? All right? So, yeah. I don't think this is kind of important. And so, this is the imaginary part, this is the real part. So whenever you have this non-minimum phase is 0, then basically they say that this is 0's magnitude, this is omega c is your crossover frequency, omega c there, for gain crossover. Okay? That gain crossover should be less than these values. Okay? These values. So then you check the size of your non-minimum phase is 0. Okay? Then you know that these are rule of thumbs. Your system, whether they can achieve stability or not. Otherwise, it's not achievable. Or in other words, this omega c should not be chosen too big. Okay? If too big, the system is not even stabilizable. You cannot make it stable. That is decided by the position of your z, your 0. Okay? So that is Bodhi's integral relationship. And I think our handout only ends up with a minimum phase. If it is non-minimum phase, the trick you need to do is to add that way, to mirror it, become minimum phase. Then you need to add another term like that. Okay? So that's why we have additional phase term here. Okay? Okay, so if you have unstable poles in the sensitivity function, remember S here is 1/1 plus L. Okay? L is the loop transfer function. We assume L is stable. open loop is called open loop stable. Then this is 0, meaning the amplitude, the amplification and attenuation should be the same. Okay? That's what we call waterbed effect. Okay, waterbed effect. You dip this high, then somewhere else will dip that high, but it's spread. The total number of water in the bed, inside the bed, is the same. So that's why it is called sensitivity dirt. Okay, sensitivity dirt. The work is not to remove, you just replace. You cannot kill it. You have to replace it to other non-important frequency range. That's the key message from Gunther Stein's body lecture, the first body lecture. It is a wonderful talk in the YouTube. You should watch, okay? To become, yeah. So now, this is a stable. You don't have any pole living on the right half plane. If you do, then the pole, real part of that add together times pi will be the amplification more than attenuation. So that's always positive, right? So attenuation, that means the attenuation, okay, is less than amplification. So that's why your system is amplified more and attenuated less. So, and that's plus is always there. Still a water bed, but there is some always bias towards amplification. We say the system is becoming harder to control, okay, because of this greater than 0. Okay, it's harder, more difficult to control. So in other words, if an open loop unstable system, we can make the system stabilized, right? But don't forget, feedback is good. You can stabilize it. But fundamentally, you still need to respect the open loop unstable pole here. Because that unstable pole imposes the sensitivity dirt. You have more dirt, basically. Okay. So it's more difficult. So if open loop, you have a system, open loop unstable, open loop stable, which is easier to control. Of course, you say open loop stable, why is it easy to control? But how to say that in mathematical language is this, in terms of sensitivity integral. Okay, it's called body's sensitivity integral. And it has a name of waterbed, it has a name of sensitivity dirt, and so on and so forth. We can stop here, and I repeated to say that. So because this part is never covered in your previous control course. If your professor does not have good frequency domain insights, they will not hammer you guys to think this way. So please, I recorded this. Let's watch it from time to time. Also watch Gunther Stein. So I hope we are very slow in making progress, but I hope you will, the basic idea will be always getting into your body and into your blood. You will never forget, okay? So there are some questions like, oh, the system, which system is harder to control? Why? You know, these are all the answers. Okay? Open loop unstable system is harder to control. And if you have a non-minimum phase 0, the system is harder to control. And that inverted pendulum on the cart, remember? That system has a unstable pole as well as a non-minimum phase 0. So it's really hard to control. And I hope you use equation and simulation to tell me the rod length is higher is easier to control, or lower is easier to control, and or mass, put a mass on top is make the system easier. You know, you can all answer that kind of question, and those mathematical analysis based on that is consistent to your personal experience as well. It's not anti-intuitive, it's very intuitive. But previously, without learning robust control, you will never get this kind of insight into the system. Okay? Again, s squared minus a squared divided by s squared minus b squared is something we feel proud of. We can tell more stories about that, okay, after we learn robust control. I'll let you go, and today, 4:30, let's meet again. I believe all of you will get access to that. I tried, I can have it. Okay, so see you at 4:30 in SE 172. Okay.